So now that we've visualized Java futures, let's go ahead and show how you can apply them in practice. And we're going to use this kind of following on to the example we just visualized to demonstrate how to multiply big fraction objects concurrently using Java futures and the Java executor service framework. So we're going to work on something called a BigFraction. BigFraction is a class that gives you arbitrary precision fraction arithmetic. And the way it works under the hood is it uses big integers for numerator and denominator. For the BigFraction, big integers can hold arbitrary precision numerators and denominators. They can be arbitrarily large up to the point where you run out of memory on your machine. And you can do various things with this. You can have a bunch of factor methods for creating reduced fractions, where a reduced fraction, something like 12/24 is 1/2, or 44/55 is 4/5, or 144 216 is 2/3, and so on and so forth. And then there's also factor methods for creating non-reduced fractions and then reducing them. So there's methods for reducing a fraction that may be non-reduced. There's also methods that do arbitrary precision arithmetic, like multiplication, division, addition, and subtraction, like I'm showing here, where 18/4 times 2/3 equals 3. And then you can also create a mixed fraction from an improper fraction. So if you have an 18/4 improper fraction, you can convert that into a mixed fraction, which would be 4 1/2. So let's take a look at how we can use Java futures to do big fraction arithmetic. And we're going to do this by using a callable, which we talked about before, and the common fork join pool. And you can see down here, this is part of my EX8 folder in my GitHub repository. So we start out with some big numbers. You can see F1 and F2 are large fractions. And we create a callable, which is a two-way task. It's a functional interface in Java 8 parlance that will return a result via a single method that takes no arguments, but you can pass in arguments here using essentially the concept of immutable, or effectively immutable, variables. We can initialize this using supplier lambda syntax, which is good old Java 8 functional programming. So we can say the callable is a supplier lambda that will create two big fractions from the strings that are effectively final. And then we can go ahead and have those things multiplied together. So F1 and F2 are these effectively final variables. Down here, we then take this task and we submit it to the common fork join pool. And that will then run that task in the common fork join pool when there's nothing else ready for it to be run. Now, what you get back when you invoke the submit call, we invoke submit, we get back a Java future to the results of that computation. And then, ... other stuff can take place. So we could go off and interact with the user. We could invoke other operations to run asynchronously, or whatever we want to do while that big fraction multiplication is taking place in the common fork join pool in the background. At some point, we're going to go ahead and get the result. So at some point, we're like, I can't wait any longer. I need to get this result. And in that case, we will either call the get method, which will block until the computation is done if it's not already done. If it's already done, you get it right back. If it's not already done, it blocks until we get it back. Or we could do a polling or timed block, where we could say, wait for up to this amount of time. So that's a quick overview showing how to program with classic Java futures. What we're going to do next, of course, is talk about the pros and cons of this approach, so you'll understand why we have Java completable futures to work around the downsides with Java futures.